the next one is a dipole is placed in a uniform electric field with its axis parallel to the field it experiences. Okay. So first I want to go to the word dipole. Okay. So what is electric dipole? Two equal and opposite charges separated by a small distance 2a constitute an electric dipole. Two equal and opposite charges separated by a small distance constitute an electric dipole. Give example: H2O, HCl, NH3 are examples for electric dipole. Okay, so how can you say the H2O is a electric dipole? So when we split H2O, it becomes H bond OH. So H has positive charge, OH has negative charge, and the bond length is 2a. So how many positive? 1. How many negative? 1. So two equal and opposite charges separated by a small distance. So it constitutes the electric dipole. So whenever we are dealing with the dipole, automatically we can go for dipole moment. So dipole moment. The dipole moment is denoted by P. The magnitude of electric dipole moment is defined as the product of magnitude of any one of the charge and the distance between them. The unit of charge is coulomb, unit of distance is meter. So coulomb meter is the unit of dipole moment. The electric dipole moment is a vector quantity. Electric dipole moment is a vector quantity because it always acts from minus q to plus q. That is electric dipole moment. Okay. So let us consider a parallel plate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 10. So let us consider two parallel plates. The positive charge are outside the first plate. The electric field is 0. Okay. Electric field outside the negatively charged plate is also 0. Between the plate, the electric field is sigma by epsilon 0. Now, the electric field is acting from positive to negative. So, this is the electric field. In this electric field, I am going to place the electric dipole. Suppose for H2O molecule. So H2O molecule becomes H bond OH. So H has positive and OH has negative. These positive charges are tried to align in the negatively charged plate, and the negative charge tries to align in the positively charged plate. Now the positive and the negative are separated. Yes, we know that electric dipole moment acting from minus q to plus q. So minus q to plus q. So it is called a induced dipole moment. Induced dipole moment. So from the diagram we can say electric field and induced dipole moment acting in the same direction. Acting in the same direction. Okay. So by using that we can classify the molecules. We can classify the molecules into non-polar molecule and a polar molecule. Non-polar molecule. The center of gravity of positive charge and the center of gravity of negative charge are coincide with each other. Coincide with each other. Then it is said to be non-polar molecule. The center of gravity of positive charge and the center of gravity of negative charge are separated by a small distance, then it is said to be polar molecule. So give example for polar molecule, H2O. So here also we deal with the same. So H2O is also a polar molecule. Okay. So non-polar. So what is non-polar? H2, N2, O2. So how we can say H2, O2, N2 as a non-polar molecule. So when we break H2, it becomes H bond H. So that positive, positive. So behind that, the negative charges are coincide. Okay. Now I am placing that H2 molecule between the electric field. Between the electric field. Now the H2 becomes H bond H, positive, positive. This positive is trying to align in the negative side. So this positive is aligned in the negative. This positive is also trying to align in the negatively charged plate. Okay. Now the negative charge which coincide with the positive is aligned in the positively charged plate. Here also we are having one negative, it's trying to align. So in general, all the positive charges are aligned in the same side. All the negative charges are aligned in the same side. Okay. So the alignment of charges in the external electric field is called a polarization. It's called a polarization. The polarization is directly proportional to electric field. So when we increase the electric field, the amount of polarization is also increases. Okay. Here, the positive and the negative are coincide, but in the external electric field, they are separated. Then it produces the induced dipole moment. So only because of external electric field, it produces induced dipole moment. So that this non-polar molecule has temporary dipole moment. Temporary dipole moment. But for the case of polar molecule, it has permanent dipole moment. Okay, do you get it now? So by using the first word dipole, so we can go for this much. Okay, right. So next one is uniform electric field. Okay, so in the previous questions we have studied electric field. Now we are adding one more word. What is uniform electric field? So uniform. So automatically we can go for non-uniform. Okay. When the electric field lines are parallel, and showing the same direction. Otherwise, the magnitude and the direction are same. The magnitude and the direction are same. Okay. Next, parallel to each other. Then it produces the uniform electric field. Here, we can go for non-uniform. The magnitude and the direction are not same. When direction may be same, but magnitude may be different. They may be parallel or not parallel. So whatever it may be, then it produces non-uniform magnetic field. Sorry, non-uniform electric field. Okay. Okay. The first one. So all lines start from the same. Okay, fine. But the terminal points are different. So they are having different magnitude. First one. Then these two are showing in the same direction, which is parallel, but it moves in this direction, So we are having different direction. Okay. So these two can be taken as parallel, but these two are not parallel. So it produces non-uniform electric field. Okay. So automatically another question arises. The positive charge or isolated positive charge can produce uniform electric field or not? No. Why? The positive charge produces the electric field radially outwards. So one is in left, another one is in right. One is at the top, another one is at the bottom. So it shows in different direction. Okay. So here at the same distances, the electric field is also different. Okay. So it's non-uniform electric field. So the negative charges. The negative charges produces electric field which is always acting radially inwards, which is also said to be non-uniform electric field. Okay. Let us consider electric dipole. Electric dipole. The electric dipole, the electric field lines always starts from positive charge and terminate at negative charge. Then between the positive to negative. Positive charge radially outwards. Here radially inwards. So each one gives different direction. So electric dipole also not produces the uniform. So it's said to be non-uniform electric field. So can you say positive and positive? So positive repel each other. So which is not uniform or non-uniform electric field. Or negative. So once again negative also repel each other. Okay, but I'll always radially inwards. Okay, it's also non-uniform electric field. So automatically another question comes. So just now we studied different cases. In that cases, the second one, the electric field due to linear wire. So gas constructed the Gaussian surface. Yes. So at the plane surface area, electric field is 0. At the curved surface area, the electric field pi equal to EA. So here the electric field becomes 0, but at this surface we are having some electric field. So there is some variation of electric field, which is also a non-uniform electric field. Plane sheet. So Gauss constructed the Gaussian surface at the front at a distance of R. Here at the back P dash at a distance of R. Here the electric field pi equal to EA. Here also the pi equal to EA. So at both it produces the electric field. Then when we are going for the final equation, E equal to sigma by 2 epsilon 0, which is independent of distance, so that we can conclude that the plane sheet produces uniform electric field. Uniform electric field. Okay. So when we are placing two parallel sheets, which is oppositely charged, so electric field is 0 outside the two sheets. Between them, electric field is sigma by epsilon 0. Here there is a variation of electric field 0 to sigma by epsilon 0, which is non-uniform. So spherical shell of radius r on the surface E is inversely proportional to r square. Outside the surface E is inversely proportional to square root of small r square. Then inside the sphere electric field is 0. So at different places it produces different electric field, which also a non-uniform electric field. Non-uniform electric field. Can you get it now? Clear it out? So now we have seen two words, electric dipole and uniform electric field. So uniform electric field, the magnitude and the direction are same and also acting in the parallel. Then it produces uniform electric field. Okay. So now we are going to combine the word dipole placed in uniform electric field. Okay. So let us consider a uniform electric field. Okay. Uniform electric field. In that, when we are placing an electric dipole, minus q and plus q separated by a distance of 2a. Now, the positive charge experiences a force along the direction of electric field, then F equal to QE. The minus Q is the charge experiences a force opposite to the direction of electric field. So F equal to minus QE. Okay, so let us consider this room as the electric field which is acting in this direction. It may be. Myself as the electric dipole. It may be positive and it may be negative. The positive charge experiences a force in this direction. Automatically, the minus Q is the charge experiences force in the opposite direction. So when it acts in this, like, then it tries to rotate. So when it rotates, then it produces the torque. So how we can calculate the torque? Torque tau equal to force into perpendicular distance. Force into perpendicular distance. So by using that force F equal to QE, perpendicular distance, then we can calculate by using making an angle theta. Then finally we can get tau equal to PE sin theta. PE sin theta. Now, by taking sin theta, we can represent in vector form. So, tau vector equal to P vector cross E vector. P vector cross E vector. So, cross product of two vector is a vector. So, torque is a vector. Torque is a vector. Now we can solve certain problems. So how we can solve? So if it is F equal to 10 Newton, then the perpendicular distance is 10 meter, then what is the torque? Okay, so torque tau equal to force into perpendicular distance. So force value is 10 and the distance value is 10. So 10 into 10, 100. Okay, torque tau. The unit of force is Newton, unit of distance is meter. So Newton meter is the unit of torque. Okay, the first one. The second one. The dipole makes an angle of 30 degree and its dipole moment is 2 coulomb meter. Then it produces the electric field of 10 Newton per coulomb. Then what is the torque? Then the torque tau equal to PE sin theta. So P, so what is the value of P? 2 into E, E value is 10 into sin theta 30. So 2 into 10 into sin 30 is 1 by 2. So 2 getting cancelled. So 1 into 10, 10. So torque tau equal to 10 Newton meter. Newton meter. Okay, the same problem may be asked like this. How? P vector equal to 2 ICAN plus 3 JCAN plus 4 KCAN. Then the electric field equal to 3 ICAN plus 2 JCAM plus 5 KCAM. Then what is the torque? Okay, so what is the formula for torque? Torque equal to P vector cross E vector. So how we can do the cross product of two vectors? That is I, J, K. Okay. For P, 2, 3, 4. For E, 3, 2, 5. Okay. So first we are going for I. Okay. So I int. So what are the remaining one? Upper. 3 5s are 15. 2 4s are 8. Okay. Second we can go for J. So minus J. So what is the remaining? 2 5s are 10. 4 3s are 12. And the last one is K. So 2 2s are 4. 2 2s are 4. 3 4s are K, K. So 2 2s are 4. 3 3s are 9. So now we can subtract. So 15 minus 8, 7. So 7 I cap minus 10 minus 12 minus 2. So minus 2 plus J cap. So 4 minus 9 minus 5. So minus 5 K cap. So like that we can go for cross product of two vector. Cross product of two vector. So when the dipole is placed, now we can add the another one. Electric dipole is placed. It produces the torque tau equal to Pe sin theta. The same word can be extended. So in a uniform electric field, when the dipole is placed, it experiences a force plus QE. Then the minus charge experiences F equal to minus QE, which makes an angle of theta so that it rotates. So when it rotates, it does some work. Here, work equal to tau into theta. Now for substituting the value of tau, Pe sin theta, then finally we can get the work done is saved as energy equal to minus Pe cos theta. Minus Pe cos theta. So by taking sign, we can go for cross product of two vector. By taking sign, we can go for dot product of two vector. Dot product of two vector. Do you get it now? Do you have any doubts? Okay, fine. So a dipole is placed in a uniform electric field with its axis parallel to the field it experiences. Okay. So let us consider the uniform electric field. Okay. In the uniform electric field, when the dipole is placed like this, so it's minus Q and it is plus Q. The dipole moment is acting from minus Q to plus Q. So in the external electric field, the dipole is aligned. Dipole is aligned or kept parallel. So in the uniform electric field, when you are keeping the dipole, it experiences tau equal to Pe sin theta. So when it is aligned or kept parallel, then theta equal to 0, then sin 0 equal to 0, 0 into something 0, so torque is 0. So what may be the option? Neither a net force nor a torque. Neither a net force nor a torque. So on the other hand, so let us consider the uniform electric field, right? Okay. In that uniform electric field, the dipole is placed perpendicular. The dipole is placed perpendicular, which makes 90 degree. Okay. So which is kept perpendicular or kept normal, where it makes an angle of 90 degree. Then sin 90 equal to 1. Then torque tau equal to Pe into 1. So 1 into Pe, it experiences only torque. So when the dipole is aligned or kept parallel in the external electric field, it makes an angle of 0. So 0 into something 0. So torque is 0. So it experiences neither a net force nor a torque. In the uniform electric field, when the dipole is kept perpendicular or normal, where it makes an angle of 90 degree, then sin 90 equal to 1. So 1 into Pe. So it experiences only torque. On the other hand, when it is placed in an non-uniform field, when it is placed in non-uniform field, in addition to the torque, it experiences a force. It experiences a force. Here you can see aligned or kept parallel. Suppose let us consider minus q and plus q of dipole moment P when it is aligned. Once again, the theta equal to 0. So sine 0 equal to 0. Then we can modify tau. Tau equal to PE sine theta plus force. So sine 0 is 0. 0 into something 0. So 0 plus force. Sorry. 0 plus force equal to force. So what may be the option? Only force. Only force. So go to the next option. So in a non-uniform field, when it is kept perpendicular or normal, where it makes an angle of theta 90, then tau, so PE sine theta plus force. Sine theta, so theta is 90, so sine 90 equal to 1. So 1 into PE plus force. So here what may be the option? Both force and torque. Okay, so for 4 options we have 4 cases. The first one is aligned, uniform electric field. Then it will be neither a net force nor a torque. Then just go to the question. A dipole, yes. In a uniform electric field, yes. Kept parallel, yes. It experiences. What may be the answer? Neither a force nor a torque. When we change the word, non-uniform electric field, then it experiences only force. When we change the word kept perpendicular or normal, then it experiences torque. Now we can change 2 words. Non-uniform electric field perpendicular, then it experiences both force and torque. Okay, can you get it now? Do you have any doubts? So successfully we completed the 5th objective. Okay.